Welcome to The Explainer. So today we're decoding a bit of a mystery that literally happens right in front of our eyes all the time, but we rarely stop to think about the incredible mechanics behind it. Think about every time you've watched a soccer match, a baseball game, or even just tossed a crumpled piece of paper into a recycling bin. Have you ever wondered exactly how long that object, that projectile, stays suspended in the air? Well, today, we're going to use the fundamental laws of physics to decode exactly how projectile motion works and learn how to predict precisely how long an object will fly. It's basically pure logic, and honestly, it is incredibly satisfying.
To make this concrete, let's set up a tangible scenario. Picture a ball resting on the ground. You run up, give it a solid kick, and boom, it launches off the ground with an initial velocity of 20 meters per second, struck perfectly at a 45-degree angle. It sails through the air in this beautiful arc and lands further down the field. So our puzzle today is answering one very specific question. Just how long was that kicked ball in the air? We're going to treat this physics problem not as some boring math chore, but as an exciting logic puzzle. And to solve it, well, we just need to uncover a few fundamental rules.
Okay, let's dive into this. First up, the setup and the secret to projectiles. First things first, let's quickly clarify our vocabulary. The total time our ball spends in the air is called the time of flight. We denote this entire, complete journey with a capital T. Imagine the path of the ball as an arc, starting at point P on the ground, reaching its absolute peak at point Q, and landing back on the ground at point R. Capital T represents that whole shebang from P to R. But here's a really neat trick about projectile motion. It is perfectly symmetrical. The time it takes to travel from the starting point, P, up to the peak at Q is exactly the same amount of time it takes to fall from Q back down to R. We call that half trip lowercase t. So capital T simply equals 2 times lowercase t. Keep that in mind because it's going to be a major clue for us.
Now, here is the ultimate secret to figuring out how projectile motion works. It's all about the divide and conquer technique. Trying to calculate a curved arc-like path all at once is just incredibly messy, so physicists simply don't do it. Instead, they split that motion into 2 completely separate parts that just happen to occur simultaneously. We break the initial velocity, which we'll call u, into a horizontal component moving straight across and a vertical component moving straight up. Notice that the horizontal velocity becomes u times cosine theta, while the vertical velocity is u times sine theta. For our puzzle today, figuring out the time of flight, we actually don't care about the horizontal forward motion at all. We're going to strictly analyze that vertical u sine theta upward motion.
Which brings us to our first logical pathway. Path A, the peak method.
So the absolutely crucial point here is what happens right at the very top of that arc. Just think about it intuitively for a second. When you kick a ball into the air, it travels upward, right? But gravity is constantly, relentlessly pulling it down, and eventually gravity wins. Right at the maximum height, our point Q, the ball actually, momentarily, stops moving upward before it begins its descent. In physics terms, at maximum height, the vertical velocity becomes exactly 0. That 0? That's our aha parameter. It is the exact anchor we need to solve the first half of our puzzle.
Let's move to and see how this builds into our equation. We start with a classic kinematic formula. Final velocity equals initial velocity plus acceleration times time, or v equals u plus at. Now let's plug in our specific vertical variables for just the first half of the trip. Our final vertical velocity at the peak is 0. Our initial vertical velocity, well, that's u sine theta. And our acceleration is gravity pulling us down, so that becomes negative g. Putting that all together gives us 0 equals u sine theta minus gt. If we rearrange that simple algebra to solve for our half-time, lowercase t, we get t equals u sine theta divided by g. But remember, that's literally only the time to reach the peak. To get our full time of flight, our capital T, we just double it. So capital T equals 2 times u sine theta, all divided by g.
Now, let's look at a completely different logical pathway. Path B, the displacement method.
Instead of looking at the peak, what if we looked at the entire trip, from start to finish? Think of it like a coordinate plane. If our ball starts on the flat ground, let's go ahead and call that the x-axis. It flies through the air, moves a considerable distance horizontally, but where does it eventually land? Right back on the ground, the x-axis. Because it starts and ends at the exact same vertical level, its total vertical displacement at the very end of the trip is 0. It hasn't permanently moved up or down at all. Let's walk through how this completely different starting assumption plays out mathematically. We'll use the formula relating displacement, time, and acceleration. S equals ut plus 1/2 at squared. Here, s is our vertical displacement, which we just established is 0. So 0 equals our initial vertical velocity u sine theta times the total time t plus 1/2 times our downward gravity, negative g, times t squared. Because every term on the right has a t in it, we can basically just factor that t out. That gives us 0 equals t multiplied by the quantity u sine theta minus 1/2 gt. Since the time of flight obviously isn't 0 seconds, the part inside those parentheses must equal 0. When we rearrange that to solve for t, we multiply by 2 and divide by g, leaving us right back with t equals 2u sine theta divided by g. Now, what's really interesting about this slide is looking at these two methods side by side. Over on the left, we use the peak method, relying on the fact that vertical velocity literally stops at the top. On the right, we used the displacement method, relying on the fact that the ball starts and ends on the ground. We took two completely distinct logical pathways, used entirely different starting assumptions, and yet they both converge on the exact same beautiful equation. Time of flight equals 2 times the initial velocity times the sine of the angle, all divided by gravity. We have officially decoded the formula.
And this brilliantly illustrates our next step, the final calculation.
It is time to bring this back to the real world. Let's look at our specific scenario from earlier again. We have a ball kicked with an initial velocity, u, of 20 meters per second. The angle of the kick, our theta, is 45 degrees, and we know the acceleration due to gravity, g, is a constant 9.8 meters per second squared. We also now have our master key, our mathematically proven equation, t equals 2u sine theta divided by g. So all that's left to do is plug our known variables right into the equation. 2 times 20 times the sine of 45 degrees divided by 9.8.
And when you crunch those numbers, you get 2.9 seconds. That's it. If you kick a ball at 20 meters per second at a 45-degree angle, it will stay suspended in the air for precisely 2.9 seconds. We didn't need a stopwatch, and we definitely didn't need a high-speed camera. By understanding how projectile motion works, dividing the horizontal from the vertical, and just applying some basic logic, we were able to perfectly predict the physical world. Honestly, that is the true magic of physics. So we've solved our puzzle for today. But you know, the best part of uncovering an equation like this is that it acts as a playground. We plugged in 45 degrees, but what if you kick the ball with the exact same power, but at a steeper angle, like 60 degrees, or maybe a shallower angle, like 30 degrees? Look back at that sine function in our formula. How would changing the angle of the kick change the time of flight? Try plugging a few new numbers in yourself to see how the physical world responds. Thank you so much for joining me on this explainer. Keep exploring, keep questioning, and I'll see you next time.